Sketch a graph of f of theta on the interval 0 to 2 pi. We'll start with the first derivative test. F prime of theta equals, the derivative of cosine is negative sine, and then the derivative of cosine squared theta, we need to use the chain rule, 2 cosine theta times the derivative of cosine theta, which is negative sine theta. This gives us negative 2 sine theta minus 2 sine theta cosine theta. There's a negative 2 sine theta in common, so we'll factor that out, leaving us with 1 plus cosine theta. Set that equal to 0, and then set each of those factors equal to 0. We get sine theta equals 0. So theta can be 0, pi, and 2 pi. And then cosine theta equals negative 1. So theta here is pi. We'll use those values to break up our interval. The interval, the first factor, second factor, f prime, and f. The first interval is 0 to pi, and then from pi to 2 pi. Then looking at negative 2 sine theta, that is negative in the first interval and positive in the second. 1 plus cosine theta is positive in the first interval and the second. Now we have negative times a positive, that is a negative, and positive times a positive, that's a positive. Since f prime is negative in the first interval, that means that f is decreasing on that interval, 0 to pi. And since f prime is positive on the second interval, f must be increasing on the interval from pi to 2 pi. And notice that there is a change here from decreasing to increasing. That means that there is a local minimum at pi. F of pi is negative 1. If we plug pi into the original f function, we can see that we get a y value of negative 1. And it looks like there are no local maxes. Next, we'll do the second derivative. So using the factored form of f prime that we have at the top of the page, we have to use the product rule. First, times derivative of the second, plus the second times derivative of the first. From here, we'll start simplifying. We'll get 2 sine squared theta minus 2 cosine theta minus 2 cosine squared theta. At this point, notice we have two different trig functions. Let's see if we can rewrite sine squared in terms of cosine squared so that all three terms have the same trig function. Remember that the Pythagorean identity gives us sine squared plus cosine squared is 1. So sine squared theta is 1 minus cosine squared theta. Then we'll just copy the rest for now. We'll distribute the 2. Next, we'll combine like terms and reorder this slightly. Negative 4 cosine squared theta minus 2 cosine theta plus 2. Next, let's factor out a negative 2, leaving us with 2 cosine squared theta plus cosine theta minus 1. From here, we can use a u substitution. Let's let u be cosine theta. We can now rewrite this as negative 2 times 2u squared plus u minus 1. This might help us see the factoring, because we want to eventually set this equal to 0 and solve. So factoring this quadratic, we get 2u minus 1 and u plus 1. Then we'll put cosine back in. 2 cosine theta minus 1 times cosine theta plus 1. Set each of those factors equal to 0. And we get that cosine theta equals 1/2 and cosine theta equals negative 1. When is cosine theta 1/2? That's when theta is equal to pi thirds and 5 pi thirds. And when is cosine theta negative 1? When theta is equal to pi. Next, we'll create a table to help us break up the intervals. We have our intervals, negative 2, 2 cosine theta minus 1, cosine theta plus 1, second derivative, and what that tells us about f. So the first interval, theta is between 0 and pi thirds. And then between pi thirds and pi, between pi and 5 pi thirds, finally between 5 pi thirds and 2 pi. So the first negative 2 is easy. Those are all negatives. In the next factor, 2 cosine theta minus 1. This might be more helpful if we think of this as comparing cosine theta to 1/2. In the first interval, cosine theta is bigger than 1/2. So we can think of that as positive in that interval. And then in the second interval, cosine theta is always less than 1/2, negative. In the third interval, cosine theta is always less than 1/2. And in the last interval, cosine theta is bigger than 1/2. So positive. In cosine theta plus 1 in the first interval, we get a plus, positive. In the second interval, positive. Third, positive. And fourth, positive. So now looking at the second derivative, we have negative, positive, positive. That's a negative. Negative, negative, positive. That's positive. Negative, negative, positive. That's positive. And negative, positive, positive. That is negative. So if f double prime is negative, that means that f, the original, is concave down on the interval from 0 to pi thirds. And if the second derivative is positive, f is concave up. And that is on the interval from pi thirds to pi. Then concave up again on pi to 5 pi thirds. And concave down on the interval from 5 pi thirds to 2 pi. And we can see that it changes concavity in 2 places. That means we have an inflection point at pi thirds. We can plug pi thirds into the original f function and see that the y value is 5/4. And we also have another inflection point at the other change in concavity, which is an x value of 5 pi thirds. Again, plugging 5 pi thirds into the original f will give us a value of 5/4. Putting together everything that we have so far, we can get a rough sketch of what this graph looks like on that interval. So we have pi, 2 pi, -1, we know that the minimum occurs at pi -1. There's a local min. We have an inflection point at pi thirds and 5 pi thirds. Those x values or those y values were a little over 1. And if we want to find the end values, if we want to know what's happening at 0, so we can plug 0 into the original f function and see that that is 3. We can also plug in 2 pi into the original f function and see that that is 3. And we get now a rough sketch of the original f. Notice that the first derivative said that it was decreasing from 0 to pi and then increasing from pi to 2 pi. And also look at the concavity. We can see that it is concave down from 0 to pi thirds and then concave up from pi thirds to 5 pi thirds, and again concave down from 5 pi thirds to 2 pi.